Next speaker in this session is Lee Rybeck with McKinstry. He's the commissioning manager for the McKinstry office in Dallas. He's got over 30 years of experience in large, some greater than 3.5 million square feet, and unique biodiversity museum projects. He is the TC79 Building Commissioning Programs Subcommittee Chair. So, Lee?
Thank you, Wade. I'm going to take just a minute here and affix the microphone. Okay, can you hear me all right? Oh, way in the back. That's good. Thank you. All righty. This program is optimization of existing buildings, much more than retro-commissioning. This particular session we'll be talking about retro-commissioning a 30,000-ton central plant. Our learning objectives for the program are the same throughout the presentations, so I won't browbeat that very much. I would like to make some acknowledgments today. First, Chris Kopak, Assistant Vice President of Facilities, the University of Arizona, whose project this will be about, who allowed us to make the presentation. Also, I'd like to mention Josh Harwood. He is a project director with McKinstry, who is actually responsible for the program I'm going to talk about, and he was unable to be here, so I'm filling in for him. So I will answer questions as best I can when we get to the end if you have them. And finally, Philip Saig, who's a business development director in that same office, who made it possible for me to have enough information to share with you today. So I would like to thank them all. So in this session, did I go? No, I'm in the right place. I threw the wrong page away. That's what happened. Okay. We're going to talk about how the client wanted to move from being a leader to an influencer. Talk a little bit about what's important in useful data. Prior speaker Nate talked a little bit about the amount of data that's available from systems and what to do with them. I'll talk a little more about that. How to prioritize in real time for what kinds of decisions you want to make. Translate that to help drive change in the organization. I'll show you some actionable results, and we'll talk about a little bit about transforming their decision making. So one of the things, and Nate alluded to it also earlier, there's kind of a flood of data available in building automation systems, especially when you see the system that our particular project was involved with retro-commissioning, very large, very complex, whole lot of moving parts, whole lot of data points. So what do you do with that data? How do you manage that? So part of what happened in this process, and I'll tell you more about that, we kind of implemented more of an active energy management rolling plan where there were some data analytics, there were some dashboards, there was some human interaction and support ongoing. Trying to make those decisions based on data, meaningful data hopefully, and looking also at financial performance. Hopefully from this session you'll get a little benefit from seeing how they were able to change to informed decision making, use real-time feedback, how they're able to make improvements in operational efficiencies, reduce energy consumption, which is usually the goal of these programs, reduce some operating costs as well, and to use some of the energy savings to help fund some additional initiatives at the campus. So as you can see, this is a very large campus. Division I university if you're into sports. 11 million square feet, hundreds of buildings, literally hundreds of staff, multiple central plants, chillers, turbines, cogeneration, 33% of electricity is produced on site. And they have numerous ice storage tanks as well in various locations as a part of the system. So talk a little bit about those central plants, hence the title of the discussion, 30,000 tons of cooling. The campus actually has 3 separate central plants, which you can see up on the screen. I won't belabor you with the details of the numbers of tons or megawatts and capacities of turbines and that sort of thing, but I think it's fair to say it's a pretty serious undertaking to try to work with this much equipment and this many locations serving so many buildings. So you have a situation where there's 3 central plants, each serving distinct areas of the campus, but also supporting an overall campus loop, a transport loop, if you will, for chilled water and hot water. So each plant has unique operating systems and different generations of equipment, making therefore each plant very unique to work on and work with, and an interesting challenge for us as a retro-commissioning firm to manage that process. So the plants were retro-commissioned using most of the standard practices. Device calibration, monitoring devices were added where necessary. BAS trending data was used very extensively with full sequential retesting once all of the operating conditions of the plant were identified. But in order to the normal challenges that you would face in a retro-commissioning project of this size, the owner shared with us a significant wave of future retirees in his very large plant operating staff personnel base. I don't know if you can see the screen very well, but you kind of get the general idea. The retirement potential of key personnel in the field was very high. So this added some urgency to bringing them a solution that would be transferable and sustainable to basically the next generation of operators at the campus. So some of the things the campus was working on in leadership development is they were working with the Leadership Academy program, which has been developed by APA. They had a supervisor toolkit. They had what they call drive-in workshops. So they were working very hard to try to help make this transition to a new generation of operators. And the previously named Associate Vice President was trying to work towards a responsibility-centered management approach, trying to make everybody accountable for their work and the things that they were responsible for. Obviously wanted to maximize operational efficiencies and make better use of the data that was available. So there's a quote up here from Chris Kopak, and it's all about the data. He referred to it as data drowning and wanting to get to a point where they could collect and sort critical information in real time. And the program that we put together for him, this is his quote, the program allows us to make informed decisions, see, understand, and monetize the results. So his facility engineers, controls, HVAC techs, energy managers, facility directors, and business managers are all going to try to get better data, be more effective, and make better decisions about everything from how to prioritize their calls, hot and cold, which equipment and actions are wasting energy, and which capital upgrades will be most important in the future. So what we put together was something we call active energy management process, and it's, if you read the description here, the concerted deployment of monitoring-based technologies and on-site building system experts to drive continuous improvements. So, you know, our industry kind of has a history of trying to automate, optimize, and outsource energy management inside buildings with I will refer to euphemistically as black box solutions. Control products, smart systems, all promising to take the burden of engineering and performance management essentially out of the hands of people and make it more automated. You know, so it's install this product and you'll be guaranteed to save X amount of energy or be X more efficient. And so what we've learned over the years is really not possible, maybe not even a good idea to take people out of the energy management equation. So the solution we put together for the campus was the best of both using the data analytics that were available and retooling them and using smart people, in other words, providing ongoing service support to the campus for this. So hoping to combine the data analytics and the strong field engineers to assist the staff with these efforts to get them cost-efficient solutions and hopefully drive deep energy savings and retain those for the long haul. So we'll talk a little bit about those as we move along. So anyway, what I wanted you to take away is that it's we're not talking about a product or a solution that you buy or install, and this is not a second building automation system or an overlay. What we're doing in this program and approach is to capitalize on the mass amounts of data they already have and turn them into methods and systems they can use and provide ongoing support. So this is totally vendor neutral. It's all about the persistence of energy savings, increasing the visibility of the systems, trying to institutionalize the technical data, optimize the staff's time so they can focus on the things that are most important, and build in some real-time monitoring performance. So conventional approach to using big data analytics is typically component-based, moment in time, still requires individual investigation, typically is very reactive, and tries to institutionalize the use of the data. So what we're trying to do with what we offer to the campus is something that's more system-based, ongoing monitoring, trying to use collective intelligence, predictive, fault diagnostic type routines, and to continue documenting those efforts and the improvements. Wow, this slide's animated. I didn't know. So I want to talk a little bit about the process that's set up, and it actually works. There's two major phases to this, the setup phase and then the continuous improvement phase. So basically, we're going to talk about the setup. You have your buildings, in our case, central plants. We want to get the data from them. As we mentioned earlier, we want to get the important data from the facility, regardless of the vendor source. We want the building automation systems. We want the meter data, monthly, interval, 15-minute, typical things you'd look for in an energy management study. And any type of manual or operational data we can get. This could be the work order system, the CMMS. It could be the documentation from the commissioning that would be on site on the land system for the building automation, those kind of things. So our purpose here was to collect and organize this data in a central warehouse and to begin analyzing the data. And some of the analysis is engineering analysis, but is assisted by some of these automated processes. So part of what we did to make this thing work for them was we wrote some algorithms and analyzed performance, tried to identify some key performance indicators that they expressed to us and turn them into tools that they could use. So we're trying to find the things that they can pay attention to, say 5 key performance indicators rather than 105. So they have the things to focus on that they are looking for. So anyway, so once the process and setup are done, then this continuous cycle of improvement can go on, where they're reviewing the information, they're implementing the improvements, they're verifying the performance, and then tracking and reporting the progress. So it's trying to get the thing into a continuous operating cycle so that they're seeing the data in a way they can use it, they're using the data, they're seeing the results, and then they can move on to hopefully the next set of key performance indicators or opportunities. So when you look at this bubble chart, what do you notice right away? That's right. Can I use the mouse here? There they are, the big bubbles. See the little ones and the big ones. So each time one of the algorithms violated the blue bubble gets a little bigger. So right away an operator can see where they might want to focus their interest if they're looking into things. So kind of right away you can see where the big issues are. I don't know if you can read this slide very well, but one issue at the CHRP plant, which is one of the 3 plants, this is the chill water flow through when chiller is off, meaning that chilled water is flowing through the chiller when it's supposed to be off and isolated. So this increases the temperature of the water unnecessarily, forces the rest of the system to work harder to cool down the water, and the valve is open when it should be closed. It's pretty much an easy fix, but on the other hand, without this process working in these dashboards focusing on these key performance indicators, it might be hard for an operator to work through the building automation system to locate the problem. So that's sort of the idea of this ongoing process. So if we continue driving through these rules, we can start visualizing them in a different way. Now this particular dashboard is a list of issues from the last slide reformatted to show a different way to look at the same data. So the chart shows us the biggest issues by the size of the bubble and color codes in the various plants. So you can see here in red that the CRB has a problem with the ice chillers are on during the off ice building schedule. So this way the operators can see the issues in a dashboard in a way that draws their attention to the important items. So another strategy in place for the program is a real-time demand management. So the active wavy line is the actual real-time demand of the plant. And the bottom line, sample about 9 days around the 4th of July last year, you can see the holiday. The red line at the top is the annual peak demand, meaning the moment in time within the last 11 months when they use the absolute most energy. And the green line is the 75% of the red line, and that's where the ratchet rate in the local utility starts. The vertical blue shaded areas are from 2 to 8 on weekdays, which are on peak times from the utility. So what we did here for the plant managers was create a blue line which predicts in real time how much demand the plant should have at any given time. So each plant has a chart, a 4-hour rolling view on a separate monitor right next to their controls monitor. So before this strategy was in place, the operators just tried to stay under the red line, the magic red line for the utility ratchet. How many of you are here from California? Okay, so you all know about utility ratchets, right? Okay. So this way, before the strategy was in place, the operators were just trying to troubleshoot and try to stay below the magic red line from the utility ratchet rate. So before the strategy was in place, they actually can save now quite a bit of money by managing the demand more aggressively by being a little bit ahead of the curve. So this is a great example of having exactly the right information at the right time to make a data-driven decision of what chillers should be turned on and off when based on that blue line. So here are the results of having the strategies in place. Highlighted a month of June's energy use and demand here. I don't know if you can see the yellow very well. And the top section's looking at the energy consumption, and the bottom's looking at the demand. So if we just focus on the demand piece, the orange line shows the demand profile in June of 15 prior to putting this process in place. The green line shows the June demand in June of last year. So as you can see, the demand profile shows a much lower demand and is in a much more logical shape to the demands of the campus. So here's what it means financially to the client. Highlighted just the month of June, and you can see the big savings in demand between 2015 and 2016. So people always, of course, want their data weather normalized, which can have an effect on demand and operational demands on the campus. But as you can see from this chart, with the weather normalization, all the data on the savings are truly due to improved performance and no drastic change in the weather. So the chart has the demand divided by degree day on the vertical and all of the days of the month in June average into a representative 24-hour period along the horizontal axis. So both June 15 and 16 are plotted, and you can see throughout June 16's weather normalized demand is consistently lower. So this is one of the ways the team at the campus can see that they are getting the results from the system and from their interactions by making better data-driven decisions. So the campus results to date, they had an initial $500,000 in operational opportunities. They developed 69 track key performance indicators as they were able to move from one set to the next. They refined their plant operating practices and operator intent. They were able to develop performance dashboards for key measures, which is something that we were helping them put together. They were able to spend some time getting their operations documented and in writing and get their sequences and emergency plans and all those things into a location where they could get to them more easily. And they identified and resolved over 100 performance improvements at the campus. So, I have a bibliography here of references that may be of use to you. And I would be happy to answer any questions as best I can, since this program was put together by some other folks in our company. Any takers? Going once? Twice?